When dealing with a 480/277 volt Y-connected system, the need for a neutral conductor and the applicability of National Electrical Code Section 230.95 depend on the types of loads being served. Let's consider a scenario where a new electrical service is installed for a wastewater treatment process. The service originates from the secondary of a new 1500 kVA utility transformer with a 480/277 volt Y connection. The secondary conductors are routed underground to a new standalone 2000 amp circuit breaker located outdoors near the transformer. The breaker's load side conductors then go to a process motor control center, or MCC, via a service entrance rated transfer switch. It's important to note that the MCC exclusively serves 480 volt 3-phase 3-wire loads. Given this setup, let's address the first question, which is, do we have to run the neutral to the motor control center? The answer is no. A neutral conductor is not required to be run to the motor control center in this specific configuration. The primary reason is that the MCC only serves 480 volt 3-phase 3-wire loads. The neutral conductor is essential when there are single-phase loads that require a return path for current. In a 480/277 volt Y system, single-phase loads are typically connected between one of the phase conductors and the neutral, utilizing the 277 volt potential. However, since the MCC exclusively feeds 480 volt 3-phase loads, there is no need for neutral conductor to provide a return path for single-phase current. The 3-phase loads are balanced and do not inherently require a neutral for their operation. Now, let's address the second question: are we bound by the requirements of Section 230.95 of the National Electrical Code? Again, the answer is no. You are not bound by the requirements of Section 230.95 of the National Electrical Code under these circumstances. Section 230.95 of the National Electrical Code specifically addresses ground fault protection of equipment. It mandates ground fault protection for solidly grounded Y electrical services of more than 150 volts to ground, but not exceeding 1000 volts to ground for each service disconnect rated 1000 amps or more. However, there is a caveat. This requirement is applicable only when the service supplies alternating current systems. It is not required when the supply is to a fire pump or services used for emergency systems. The critical factor in determining whether Section 230.95 applies is the presence of 277 volt single-phase loads. If there are no 277 volt single-phase loads connected to the system, then Section 230.95 does not apply. The rationale behind this lies in the purpose of ground fault protection. Ground fault protection is designed to detect and interrupt low-level ground faults that may not be high enough to trip a standard overcurrent protection device such as a circuit breaker or fuse. These low-level ground faults can persist and cause equipment damage, overheating, and potentially lead to electrical fires. In systems with 277 volt single-phase loads, ground faults are more likely to occur due to the higher voltage to ground. The presence of a neutral conductor also provides a path for ground fault current to return to the source, making ground fault detection more effective. However, in a system that exclusively serves 480 volt 3-phase loads without any 277 volt single-phase loads, the risk of ground faults is significantly reduced. The absence of a neutral conductor further minimizes the likelihood of ground fault currents. Therefore, Section 230.95 is not applicable in this specific scenario. In summary, for a 480/277 volt Y-connected system serving only 480 volt 3-phase 3-wire loads, a neutral conductor is not required to be run to the motor control center, and the requirements of Section 230.95 of the National Electrical Code do not apply. This is because the neutral conductor is only necessary for single-phase loads and ground fault protection is primarily intended for systems with 277 volt single-phase loads. It is always crucial to consult the latest edition of the National Electrical Code and local amendments to ensure compliance with all applicable requirements. Additionally, it is recommended to consult with a qualified electrical engineer or inspector to verify the specific requirements for your installation. Let's delve deeper into the technical aspects of why the neutral conductor is not necessary for purely three-phase loads and further clarify the conditions under which ground fault protection is mandated by Section 230.95 of the National Electrical Code. First, let's revisit the function of the neutral conductor in a 480/277 volt Y system. The 480/277 volt Y configuration is derived from a three-phase transformer where the three-phase windings are connected in a Y or star configuration. The center point of the Y is grounded, creating the neutral point. The voltage between any two-phase conductors is 480 volts, while the voltage between any phase conductor and the neutral is 277 volts. This allows for the supply of both three-phase 480 volt loads and single-phase 277 volt loads from the same system. The neutral conductor provides a return path for current in single-phase circuits. When a single-phase load is connected between a phase conductor and the neutral, current flows from the phase conductor to the load and returns to the source via the neutral conductor. Without the neutral conductor, the single-phase circuit would not be complete, and the load would not operate. However, three-phase loads do not require a neutral conductor for their operation. Three-phase loads are connected to all three-phase conductors, and the current flows in a balanced manner between the phases. In a balanced three-phase system, the currents in the three-phase conductors sum to zero at the neutral point. Therefore, there is no net current flowing through the neutral conductor, and it is not needed for the operation of the three-phase load. In the scenario described, the motor control center serves only 480 volt three-phase three-wire loads. This means that all the loads connected to the MCC are three-phase loads, and none of them require a neutral conductor. Therefore, it is not necessary to run a neutral conductor to the MCC. Now let's examine the requirements of Section 230.95 of the National Electrical Code in more detail. Section 230.95 mandates ground fault protection of equipment for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 1000 volts to ground for each service disconnect rated 1000 amps or more. This requirement is intended to protect equipment from damage due to low-level ground faults. Ground faults occur when current flows from a phase conductor to ground, either through a fault in the equipment or through accidental contact with the grounded surface. These low-level ground faults may not be high enough to trip a standard overcurrent protection device, such as a circuit breaker or fuse, but they can still cause significant damage to equipment, overheating, and potentially lead to electrical fires. Ground fault protection devices are designed to detect these low-level ground faults and interrupt the circuit before significant damage occurs. They typically operate by monitoring the current balance in the phase conductors and the neutral conductor. In a healthy system, the current in the phase conductor should sum to zero, and there should be no current flowing in the neutral conductor. However, when a ground fault occurs, current will flow from a phase conductor to ground, creating an imbalance in the phase currents and causing current to flow in the neutral conductor. The ground fault protection device detects this imbalance and trips the circuit breaker, interrupting the flow of current and protecting the equipment. However, as previously mentioned, Section 230.95 only applies when the service supplies alternating current systems. It is not required when the supply is to a fire pump or services used for emergency systems. More importantly, the application of Section 230.95 is contingent upon the presence of 277-volt single-phase loads. If there are no 277-volt single-phase loads connected to the system, then Section 230.95 does not apply. The rationale behind this exception is that systems without 277-volt single-phase loads are less susceptible to ground faults. The higher voltage to ground in 277-volt systems increases the risk of insulation breakdown and ground faults. Additionally, the presence of a neutral conductor in 277-volt systems provides a path for ground fault current to return to the source, making ground fault detection more effective. In contrast, systems that exclusively serve 480-volt three-phase loads without any 277-volt single-phase loads have a lower risk of ground faults. The absence of a neutral conductor further reduces the likelihood of ground fault currents. Therefore, Section 230.95 is not required in this specific scenario. To further illustrate this point, consider the following examples. Example 1. A manufacturing facility has a 480/277-volt Y service with a 2000 amp main disconnect. The facility uses 480-volt three-phase motors for its production equipment and 277-volt lighting. In this case, Section 230.95 would apply because the service has a disconnect rated 1000 amps or more and serves 277-volt single-phase loads. Example 2. A data center has a 480/277-volt Y service with a 3000 amp main disconnect. The data center uses 480-volt three-phase power distribution units, or PDUs, to supply power to the servers. There are no 277-volt loads in the data center. In this case, Section 230.95 would not apply because there are no 277-volt single-phase loads. Example 3. A hospital has a 480/277-volt Y service with a 1600 amp main disconnect. The hospital uses 480-volt three-phase equipment for its HVAC system and 120-volt receptacles for general use. The 120-volt receptacles are supplied by step-down transformers. In this case, Section 230.95 would not apply because the 120-volt loads are not directly connected to the 277-volt system. They are supplied by separate transformers. In conclusion, the decision of whether to run a neutral conductor to a motor control center and whether Section 230.95 of the National Electrical Code applies depends on the specific characteristics of the electrical system and the types of loads being served. For a 480/277-volt Y-connected system serving only 480-volt three-phase 3-wire loads, a neutral conductor is not required, and Section 230.95 does not apply. However, it is essential to consult the latest edition of the National Electrical Code and local amendments to ensure compliance with all applicable requirements. It is also recommended to consult with a qualified electrical engineer or inspector to verify the specific requirements for your installation. Let's consider some additional factors that might influence the decision of whether to run a neutral conductor to the motor control center, even if it is not strictly required by code. Firstly, future expansion. If there is a possibility that the motor control center may serve 277-volt single-phase loads in the future, it may be prudent to run a neutral conductor to the MCC during the initial installation. This would avoid the need to run a separate neutral conductor later, which could be more costly and disruptive. Secondly, voltage drop. In long cable runs, the neutral conductor can help to reduce voltage drop, especially under unbalanced load conditions. However, in most cases, the voltage drop in a three-phase system is not significantly affected by the absence of a neutral conductor, provided that the system is reasonably balanced. Thirdly, harmonics. Nonlinear loads, such as variable frequency drives, can generate harmonic currents that flow in the neutral conductor. If the motor control center serves a significant number of nonlinear loads, it may be necessary to run a neutral conductor to mitigate the effects of harmonic currents. However, in many cases, harmonic filters or other mitigation techniques can be used to reduce harmonic currents without the need for a neutral conductor. Now, let's explore some of the exceptions and nuances related to Section 230.95 of the National Electrical Code. Firstly, multiple disconnects. If a service has multiple disconnects, each rated less than 1000 amps, but the sum of their ratings exceeds 1000 amps, then Section 230.95 may still apply. The specific requirements for multiple disconnects are outlined in the National Electrical Code and should be carefully reviewed. Secondly, healthcare facilities. Healthcare facilities have special requirements for ground fault protection, as outlined in Article 517 of the National Electrical Code. These requirements may differ from the general requirements of Section 230.95 and should be carefully considered. Thirdly, industrial establishments. Industrial establishments may have different requirements for ground fault protection depending on the specific nature of their operations. It is important to consult with a qualified electrical engineer or inspector to determine the appropriate level of ground fault protection for an industrial establishment. Let's now discuss the practical implications of not running a neutral conductor to the motor control center. Firstly, cost savings. Eliminating the neutral conductor can result in cost savings in terms of materials and labor. The neutral conductor is typically the same size as the phase conductors, so eliminating it can reduce the amount of copper required for the installation. Secondly, reduce conduit size. Eliminating the neutral conductor can allow for a smaller conduit size, which can further reduce costs and simplify the installation. Thirdly, simplified wiring. Eliminating the neutral conductor simplifies the wiring of the motor control center and reduces the number of terminations required. However, it is important to ensure that all equipment is properly grounded and bonded to provide a safe and reliable electrical system. It's important to note that local codes and regulations may have additional requirements beyond those outlined in the National Electrical Code. It is always essential to consult with a local electrical inspector to ensure compliance with all applicable codes and regulations. Furthermore, the design and installation of electrical systems should always be performed by qualified and licensed electrical professionals. These professionals have the knowledge and experience necessary to ensure that the system is safe, reliable, and compliant with all applicable codes and regulations. In addition to the National Electrical Code, other standards and guidelines may provide useful information and recommendations for the design and installation of electrical systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the National Electrical Manufacturers Association, or NEMA, and Underwriters Laboratories, or UL. These standards can provide guidance on topics such as grounding and bonding, overcurrent protection, and harmonic mitigation. In summary, the decision of whether to run a neutral conductor to a motor control center and whether Section 230.95 of the National Electrical Code applies is a complex one that depends on a variety of factors. These factors include the types of loads being served, the size of the service, the presence of 277-volt single-phase loads, and local codes and regulations. It is essential to carefully consider all of these factors and consult with qualified electrical professionals to ensure that the electrical system is safe, reliable, and compliant with all applicable requirements.